is to determine, to draw the log magnitude and phase characteristics of lead compensating network, as well as log magnitude and phase characteristics of lag compensating network, and to compare the experimental results with your theoretical results. So actually you must, before coming to the laboratory itself, you must draw the Bode plot for both the lag compensator and lead compensator, taking a transfer function, and come to the laboratory. After coming to the laboratory, after doing the experiment, depending on the values that you get, you have to plot the Bode plot for the values obtained in your observation, and you must compare those two Bode plots. So the apparatus required are, you need a voltmeter of 0 to 5 volts, which is of rectifier type. You need a signal generator. You need a CRO. You need a circuit board of lag compensator, as well as a circuit board for lead compensator. So you need here two circuit boards. One is for lag compensator, one is for lead compensator. You need BNC probes. You need actually two BNC probes, because in the CRO you will be having, you have to give X plate connection as well as Y plate connection. So X plate connection must be given to the input side, that is on the side in which to which signal generator is connected, and Y plate connection must be given to the output side. So you need two BNC probes, and you need some connecting wires. So this is the circuit diagram of this lead compensator. So you need two resistors and one capacitor. The resistance values are 18 kilo ohms and 330 ohms, and the capacitance that you require is 2 microfarad. And actually in our laboratory, these resistance and capacitance components are already fixed on the board. You can design your own lead compensator network taking a breadboard. You can take a breadboard, and on that breadboard you can take these components, resistance components and capacitance components, and as shown in the circuit diagram, you can give connections on the breadboard and you can do the experiment. Okay, so you can see here on the input side, a voltmeter of 0 to 5 volts is connected here, and signal generator is also connected on the input side. Okay, so of course we are showing here CRO on the output side. Why? Because we are going to see the output, that is Lessage's pattern on the CRO. That's why we have written a CRO on the output side. But from the CRO, X plate of the CRO must be connected to the input side of this circuit, and Y plate must be connected to the output side of this circuit. Similar to your lead network, lag network. So in the lag network, resistance of 8.2 kilo ohms is connected in series to this capacitance of 2 microfarad, and you need one more resistor of 18 kilo ohms. So you can take a breadboard and you can give connections on the breadboard. But in our laboratory, already these elements are fixed. They have been connected on a board. So you need to give only input and output connections. So you need a rectifier type voltmeter to be connected on the input side. On the input side, signal generator must also be connected, and CRO X plate must be connected to the input side, and Y plate must be connected to the output side. Okay, so this is actually in our laboratory, this is a function generator, that is signal generator. So this is somewhat similar to your signal generator that we use in the laboratory. Okay, in our laboratory we have a digital display type signal generator, as well as analog signal generator. That is frequency can be displayed on the screen, or you can manually vary the frequency using the signal generator. So supply input from the signal generator from this red knob and the black knob must be given to the input side here. Okay, this side. This is our signal generator which I am showing you here. So okay, so it must be given to the input side, and we must set a sine wave. If you see in this signal generator, you have a ramp wave, square wave, and sinusoidal wave. So we are going to give sinusoidal input here to the signal generator. And frequency, we are going to continuously vary the frequency in this segment. So you can see a scaling wheel is there here. Okay, so this disc which is having proper scaling here, this disc is used to vary the frequency, and you can set the range of the frequency. You can see here this first knob 1, okay, this is 0.1, this point is not visible here. Okay, so this is 0.1 hertz. Okay, 0.1 into, if if you see here, this indication is on 10. Okay, this indication is on 10, so 0.1 into 10, that is 1 hertz. Okay, so similarly you can set the range and you can vary this scaled wheel or disc. Okay, and you will get the desired frequency can be set here. Okay, you can if you want suppose if you want 2 kilohertz. Okay, if you want 2 kilohertz, so if you see here, you must press this 1K knob, and you must rotate this disc using this knob which is available here, and this 2 which is here, if you carefully observe, this 2 must be below this indicator. Okay, now in this experiment, after giving connections, okay, after giving connections means let us also have this, this is our CRO. Okay, so if you carefully observe here, channel 2 X is written. If you carefully observe, I'll expand the screen and I will show you. If you carefully observe, here channel 2X is written, here channel 1 Y is written. So channel 2 knob, this is BNC probe must be given here, this must be connected here. From here you must give it to the, from channel 2. Okay, that is X plate. Okay, from channel 2 you must give it to the input side of that circuit board, and from channel Y you can see already a BNC probe is connected here. Okay, it must be given to the output side of this, from this CRO. Okay, and since we are going to see the Lessage's pattern in this experiment, okay, so the magnitude or the amplitude, in order to vary the amplitude, these two for channel 1 and 2, these two knobs are used. So we will fix it to some constant value. Usually in our laboratory we will set it as 1 volt. Okay, amplitude as 1 volt on both the channels, because we are using both the channels here, isn't it? The BNC probes are connected to both the channels, so amplitude is fixed, and even the time is also set. Okay, this is our time knob. You can set any desired value using this time knob. Okay, okay, so this is our input supply power switch for the CRO. Similarly, for function generator, this is our power switch, main power switch of this function generator. Okay, so you can see here, I didn't show you this. Here also, as you vary the knob, this pointer is location is varied, and you can set the desired frequency by varying this knob. Okay, so and you can set the desired sine wave or square wave or ramp wave depending on the requirement. Okay, so initially after giving connections, we must set 1 volt in the signal generator. Okay, so you have connected a voltmeter across the input side. On the input side, you have connected a voltmeter. So the voltmeter reading should be 1 volt. Okay, so in order to vary the amplitude of the input voltage, you must use this knob. You can read here amplitude. Okay, you can read here amplitude. You just vary this knob. As you vary this knob, what will happen is the voltmeter reading will vary. Okay, and you can set 1 volt. So throughout the experiment, as you vary the frequency, the amplitude input voltage may vary. Okay, so you must gradually, means while doing the experiment, you must make sure if the voltage varies, by varying this amplitude knob, you must set the voltage to 1 volt. Okay, so after giving connections, initially we will set 1 volt by varying this amplitude knob, and the input signal that is given is sinusoidal signal wave. So you must press this sine wave knob. Okay, you must press this sine wave knob and vary the amplitude knob to set 1 volt. Okay, so and initially we will start with 20 hertz frequency. So 20 hertz I want, so I have here uh, 10 hertz knob is there. I'll press this 10 hertz knob. Okay, so I'll press this knob, 10 hertz knob, and I will vary this disc, and I'll make sure this 2 is exactly below this indicator. Exactly below this indicator. I'll keep this 2 exactly below this indicator. If my function generator is of this type, then I'll make sure that this red line is on this 2. Okay, this red line is on this 2, and this pointer of this knob is at 10. Okay, so it's not a big issue. You can, while doing the experiment, you'll get the idea. Okay, so initially we will start with 20 hertz frequency. So set press 10 on this frequency range in the function generator, and make sure this 2 is exactly below this indicator. So 2 into 10, you will get 20 hertz. Okay, so now after you have set the input, you have set 1 volt using this function generator and frequency 20 hertz. Okay, now you have already, before giving supply itself, you have given connection, X plate connection to the input side, X connection to the input side, and Y plate connection to the output side. Set this CRO in XY mode. Okay, there will be an XY mode knob here. Okay, there will be an XY mode knob or switch, I can say. You just press that knob. Okay, as soon as you press that XY mode knob, what will happen is, okay, Lasage's pattern will be displayed on the screen of the CRO. You will get somewhat like this. Okay, you can see this pattern on the screen. Okay, this is what you can see. So in order to have much more clarity, I'm showing you another image. Okay, so this is my pattern. Okay, now, so whatever pattern that you get here, okay, so from this pattern, you must note down the X in, XP, Y in, YP values. X in is the Lasage's pattern will cut the x-axis, that is this x-axis. Okay, this is our x-axis, or in this is our x-axis. Okay, this is x-axis, this is y-axis. I hope you are able to see the x-axis and y-axis. You just carefully observe in the middle. Okay, this is our x-axis, this is our y-axis. Okay, so it is cutting this x-axis at some point that you assume it as, you consider that value as x in value. Okay, from the tip of this pattern, draw a line, vertical line, which will meet this x-axis at some point that you assume it as xp. Okay, so this Lasage's pattern will cut this y-axis. This is our y-axis. It is cutting this y-axis at some point. You consider that as y in. Okay, from the tip of this pattern, draw a horizontal line. It will cut the y-axis at some point. Assume it as yp. Okay, now in your observation table, Okay, any observation table, note down the, initially we have assumed 20 hertz frequency, write down the frequency, omega is equal to 2 pi f, you can calculate it later on after completion of your experiment, write down x in value, xp value, y in value and yp value. Okay, now go to the function generator. Now increase the frequency. Okay, increase the frequency to earlier this exactly this indicator was about 2. Now you can go for 40 hertz. Okay, so make sure 4 is below this indicator. Okay, you just vary this knob. So you will get 40 hertz. Okay, so for 40 hertz frequency, 4 into 10. You have already pressed this 10 now. Okay, for 40 hertz frequency, you just check the voltmeter reading. Okay, whether the voltmeter which you have connected on the input side, okay, this voltmeter which you have connected on the input side, is it showing 1 volt or not? If it is not showing 1 volt, if it has changed, vary this amplitude knob. Okay, vary this amplitude knob. As you vary this amplitude knob, uh, your voltage, you can set the voltage to 1 volt. Okay, and you, since you have varied the frequency, the pattern on the screen might have changed. Okay, the pattern might have changed. Okay, so since the pattern has changed, again note down x in, xp, y in and yp from the CRO. Okay, and you just note it down in the tabular form. Frequency now we have assumed 40 hertz, x in yp, x in xp, y in yp, note it down. And similarly, you vary the frequency. So since you have pressed here 10, after 40 you can go for 60, next 80, next 10. So 10 into 10 it is 100 hertz you have got. Now press 100 hertz knob. Okay, now press 100 hertz knob and start with 200 hertz. Okay, so now again this indicator should be about 2. Okay, you just vary this knob to send this 2 below this indicator. So 2 into 100, you will get 200. Okay, again you just check the amplitude voltage value and the voltmeter. If it is not showing 1, vary this. If it is showing 1 volt, no need to vary this amplitude knob of the function generator. Okay, and so on. You will vary. You can vary the frequency gradually. Okay, up to 1 megahertz. Okay, depending on it need not be. You can take approximately 10 readings. That is more than sufficient. Okay, with the 20 hertz frequency difference from one reading to another reading. Okay, so gradually you just vary the frequency, keep maintaining 1 volt constant in the voltmeter by varying this amplitude knob. Okay, from the CRO. And after noting down all the values in the tabular form, determine the gain value, that is 20 log yp by xp. So you have xp value, yp value, determine gain. Similarly, determine the phase value, that is sine inverse of x in by xp. You have x in and xp value, so you can determine the phase. So you will get some phase values, you will get some gain values, and omega, you 2 pi f, you calculate omega value. So you have some range of omega values, gain values, and phi values. Take a semi-log graph sheet, okay, and you plot the graph. So procedure for lag compensator as well as for lead compensator is same. Okay, for both lag compensator and lead compensator, procedure is same. Connections are same. Okay, only the internal connections will vary. The R and C values as well as their connections will vary. That's all, nothing else. Input connection and output connections for both the compensators are same. Okay, and you have to plot two tabular forms. One is for lead compensator. One is for lead compensator. Another is for lag compensator. Okay, you have to plot two tabular forms, one for lead and one for lag. And so for lead compensator, the magnitude plot that you will get, it will be somewhat like this, and phase plot. Okay, you might be already knowing these plots. Why? Because you already know the subject, you have already learned it in your third year first semester. Okay, this is the magnitude plot and lag phase plot for the lag compensator. Okay, that's all. Okay, so the result is the log magnitude and phase characteristics of lead and lag compensators are plotted by conducting a suitable experiment. Okay, already you might have already done the theoretical calculations by considering some transfer, taking a transfer function, and you can compare your graph, theoretical graph with your practical graph. Okay, it's an easy experiment, very simple experiment. Only the thing that you have to do is you must compare the lesser, you must get the pattern on the CRO, you must carefully note down the values.